Okay, if you are in green group, the ones on this video we did in class, at least some portion of them, so you could probably let this play through until at least where you need to see. So this should be Chemistry 25CBlake and week 25A video went up into here somewhere, and then 25B went up to number 40, I think. And I think we're ready for number 39, and then we went over those in class on Tuesday, I think. So, yeah, we finished up with number 40. So let's go to the next one here. This one, number 39, you do not have a central atom. It is C2H4, which is ethene. So these get progressively more sticky as you get a little bit farther. So we got C2H4. The first thing you do is you write down all the atoms. You have a carbon, and a carbon, an H, and an H, and an H, and an H. In your periodic table, and let me see if I can pull one up here. It's not that one. No, don't worry about it. I know where there is one. I just got to get to it. Okay, here's one. We have carbon in the 1, 2, 3, 4th column, has 4 valence electrons. Hydrogen is up here, has 1 valence electron. So carbon has 4 apiece. Hydrogen 1 apiece. Then you add up what you got. So far we don't have a charge on this one at this point. If you had a charge on it, you'd have to do a little dance right here. 1, 2, 3, 4, 8, 12. We need our answer to be 12 electrons. Next, you pick a central atom. Well, you wouldn't know it on this, but you don't have one central atom. Each carbon is going to be somewhere near the center. And then we have to split up the hydrogen. And you wouldn't know this one because hydrogen has to go 2 of them on this one and 2 of them on each carbon. And you could put, and then you have to do shared pairs. So do shared pair here, 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 here. So I wouldn't give you this probably question on a test because you don't have one central carbon. Now, you don't want to put 3 hydrogen on one and 1 on the other. It has to be 2 and 2. And your hydrogen could be here and here, and here and here, or here and here. And the hydrogen on this carbon could be here and here, or here and here, or here and here. That won't matter. This is really an organic chemistry example. Organic chemistry students would be expected to work through this because ethene is a very simple organic compound. Once you share, put your shared pairs in, then everybody gets 8. Now there are some exceptions to that, and I want to mention those now and again later. Pretty much everybody gets 8. These get 8. These already have 8, so they don't do reactions, so we don't have to make molecules. So they don't make molecules, so we don't have to talk about these this chapter. In fact, we're pretty much done talking about the noble gases. These end up with 8. These end up with 8 valence electrons. These end up with 8 valence electrons. These end up with 8 valence electrons. But once you go to the left of the carbon family, the boron family does something called sp2 hybridizes. They end up with 6, so they don't follow the octet rule. So all that stuff we've been telling you for the last year about they want to end up with 8 valence electrons, well, these don't. So there's a big, now we're going to start looking at where the rules are broken. These end up with 6 valence electrons, these end up with 4 valence electrons, and these end up with 2 valence electrons, just like the hydrogen at the top. We'll also look at a couple of examples where you end up with more than an octet. With phosphorus, you can have 10. Sulfur, you can have 12. Some of these halogens, you could have 10. So there are lots of exceptions, but most of them still use 8. Okay, back to here. So my carbon is supposed to end up with an 8, so I need a pair here and a pair here. What's the next step? Everybody always forgets the next step. The next step is to count and make sure our pairs add up, and if they don't, we have to change something. 2, 4, 6, 8, 10, 12, 14. That's too many. You should never have too few. If you have too few, either you messed up the charge up here or something went wrong. So what do you do when you have too many? When you have too many, you have to delete pairs and move pairs. Okay, 14 electrons. And I gotta take 2 electrons out. I gotta delete a pair. That's easiest to do off the central carbon. Both these are central carbons. You don't have one central carbon, so I'll take this pair out, move this pair up. And once we do that, I have carbon looks like this with hydrogen, hydrogen, double bond, carbon, hydrogen, hydrogen. I can replace the shared pairs with sticks. So I'd have it H, C, H, double bond, C, H, H. No extra lone pairs left. And the last thing to do is do something called valence shell electron pair repulsion, which is a lot of words that means this. You're not going to have your electrons bunched up at 90 degrees and 90 degrees and then have a big gap over here of 180 degrees. Likewise, you're not going to have a big gap of 180 degrees and have your electrons that are all trying to repel each other all bunched up into 90 degrees, 90 degrees. These will move out and try to repel each other to the extent they can, and so you'll end up with your ethene molecule looking like this. Now, to do the Lewis structure, you don't need to go this extra step. This is your Lewis structure right here. Lewis structure. But you do need to be able to go onward. Okay, since all this stuff is in the next page, oops, I didn't mean to cut that. Insert page after I meant to clear annotations. Okay, the next one was nitrite ion, NO2 minus. This has a charge, so we got to do something different. So we have to make a listing of the atoms: nitrogen, oxygen, oxygen. Then you got to know what families they're in. So nitrogen is here, takes 5, has 5 valence electrons. Oxygen is here, or I'm sorry, nitrogen is here, takes 3. We don't care about that. It has 5, so it's got 5 valence electrons, 5 dots. Oxygen is here, has 6 valence electrons, so we need 6 dots. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6 for the oxygen. 1, 2, 3, 4, 5, 6 for the other oxygen. Then we add. That's 6 and 6 is 7. That's 17 electrons, and it's got a negative charge. So right here we add 1 electron for a total of 18. This step you're going to have when you have a polyatomic ion that's negative, you have to add electrons. I gave you an example already where if it's a positively charged, you have to take an electron away, and ammonium was an example there. It might have been hydronium ion. I don't remember which one it was right now. Okay, so next we have to pick a central atom. That's the odd guy out. He's closer to carbon. So we'll put nitrogen there. the oxygen on either side, make it the central atom, then skeletal structure. We need shared pairs put in. Then we give everybody 8. These guys are in the columns where they are going to have 8. And you could say, well, what about phosphorus and sulfur were down here can do more than 8? Yes, but you can't do that with ones in the second period. In order to be able to do that, you have to be in the third period so that you can take electrons out of or put electrons into the d orbital. So this problem you don't have with second period elements, and right now we're dealing with that in organic chemistry, and the question is why? Well, this is the answer. Okay, now make sure everybody gets 8. 2, this one has 8. Put 2 here, oh no, 2 here and 2 here, and nitrogen has 8. 2 here and 2 here and 2 here, and oxygen has 8. Now what do? We have to add again. So there's 8, 16, 18, 20. Uh-oh, it's not right. Too many electrons. So we will delete a pair and move a pair. Just take them off of the central atom and you'll have fewer problems. You can take them off up here, it doesn't matter, and then move one of these pairs in, and it doesn't matter which side you move it from. You can even do it from the ends, but you have to be able to visualize that. Let me move this pair in here. If I do that, I have O dot N O. And now I have 8, 10, 12, 14, 16, 18. And that's what I want. So I replace the shared pairs with sticks and leave the lone pair, O, like that. Now this is a resonance type of deal. It's going to end up taking this shape because that electron up there, pair up there, is going to push these down. Okay, now that's 120, 120, 120, close to, it won't be exact. And that's what you get. But that's going to be resonance. Let me turn the page here. This is what it's going to end up doing. You have to put, first of all, I didn't do this on the last page, but you have to put this in a bracket, give it a negative charge, put this in a bracket, give it a negative charge, because that negative charge is shared among the whole thing. So I forgot that part. You can't forget that. It's not right until you put that in there. Also, it's resonance, so it acts like it's a blend of both of these two at the same time.